Well, so far we have seen some intuitive definition of what the divide and conquer strategy is, and we have seen quite in some detail merge sort. As I said before, go code it, go and figure out what its computational cost is. From now on, we're going to be speaking about Quicksort, another exciting divide and conquer recursive sorting algorithm. And we will be doing this not with slides like in merge sort, but with the code. So we are going to see the whole code. Before we do that, let's speak about the strategy that we are going to follow for Quicksort. Basically, this is the main strategy. You have it here in some detail, but we are going to have our list, and remember, we need recursive calls here, and we need to divide the data so that we can conquer it later. So the first thing that we are going to do is decide how we are going to divide this data. Specifically, we are going to choose an element that we will call the pivot, and we will find out mostly where that element should go. But we will do that through figuring out what elements in the list are bigger and smaller than the pivot. Specifically, bigger or equal and smaller. So we are going to break down, choose one element, pivot, and divide all the elements between bigger or equal and smaller than the pivot. Then we will put the pivot in its correct position and put all the smaller elements on the pivot before it and all the bigger elements than the pivot after it. Okay? An important distinction here is that these elements that we put either before or after the pivot will hold the condition that they will be smaller or bigger than it, but they will not be sorted themselves. Okay, they will only be a little sorted in this sense that they are smaller than the pivot, which is in the correct position. It's the only element sorted at this point, smaller or bigger, but they among them will not be sorted. This idea of choosing a pivot and heaping all the smaller elements before it and all the bigger elements after it is called partitioning the list, and we will have a particular function that does that, and we will spend most of our time in it. Okay, and then if I suppose that I have a function that does this, choose an element, put it in the right place, and all the smaller elements before it and all the bigger elements after it, then if I have that, then it's pretty easy to set up my Quicksort algorithm thanks to the magic of recursion, because these smaller elements and bigger elements are going to be my recursive calls. Okay, so let's suppose that I have a Quicksort function that receives a list and the first and last elements that I want to sort. And let's imagine that I have a partition function that does what I said before. So after I have run this, I have changed my list so the pivot is in the right position, and then from the first element to the pivot, I have the smaller elements and the pivot, and from after the pivot to the last element, I have the bigger ones. So I just need to recursively call Quicksort. Okay, and here I would also have a base case where again my lists are one element long. Here you have it, and they are because of that sorted. Okay, so if my lists, if last and first are the same element, if my lists are just made up of one element, I just return. I don't do anything because my list is properly sorted. And then in the recursive case, base case, recursive case, I have this behavior. I have a partition and I have two recursive calls. Partition puts a pivot in its correct position and smaller elements than it before it, bigger elements than it before, after it, and those two groups are not properly sorted, and that's what happens when I do my recursive call. Okay, I can play around a little bit with my code because this return thing is not too pretty, and I end up with this code that does exactly the same thing. Okay, so this is a general idea of how the quicksort algorithm will work, and now I'm going to go a bit deeper into the partition function.